Hello friends. Today we will learn how to convert Fischer open chain formula into cyclic formula. So uh, we will take one by one. So firstly, we will take this is the open chain structure of D-glucose. So this can be converted into the cyclic formula, and first of all we are converting it into the Pyranose form, and Pyranose form is the six-membered ring. This is six-membered ring. So for the six-membered, this is the first carbon, this is second, third, fourth, fifth and sixth. So five carbon and one oxygen will form one cyclic ring. So that will be your six-membered ring. So here this fifth carbon OH group will attack here nucleophilically, and there will be nucleophilic addition, and we will get the cyclic structure. So here we will get the newly generated chiral center. So now the structure will be like this: 1 2 3 4 5. There are total 5 chiral centers. This is HOH, this is D because OH is on the right hand side, and this is HOH, and this is third carbon OH on the left, and this is second carbon, and this is the first carbon here. So here this is basically this one. Now this was the fifth carbon OH, and this is the oxide ring, and this is the carbon 1, which is also called the anomeric carbon. And at the anomeric carbon, this is the newly generated chiral center, and because this is the newly generated chiral center, so there will be two two enantiomer, and in one isomer the OH will be on the right hand side, in another the OH will be on the left hand side. So another isomer you can go 1 2 3 4 5, you can draw like this, and here this is fifth carbon and CH2OH, this is H, HOH, HOH, and here at the anomeric carbon, which is C1, newly generated chiral center, here OH is on the left hand side, this is OH on the right hand side. So right hand side, this will be the alpha D glucopyranose. Pyranose is for the six-membered ring, and alpha is when it is on the right hand side. The more electronegative group OH is on the right hand side at the anomeric carbon, that will be alpha. And if it is on the left hand side, this will be beta D glucopyranose. So this is, now these two are the Fischer structure, Fischer projection formula, cyclic formula of the alpha and beta D glucopyranose. Now next is how to convert the Fischer cyclic structure into Haworth formula or Haworth structure. Now this is the cyclic structure in the Fischer formula. This is two-dimensional. There are two types of bonds. One are vertical bonds, another are horizontal bonds. So here, whenever we convert it into the Haworth formula, we always uh, draw the ring in one plane, like this is the six-membered. So here this part of the ring is toward the observer, means towards us, and now the other all the groups will be in the vertical position. So this is the horizontal ring in the horizontal plane, and this all the bonds or groups will be in the vertical planes. So here this is oxide ring is put always in the back side, and this is the carbon 1 or anomeric carbon, which is placed on the right hand side. So this was the carbon 1, which is the anomeric carbon. And here whatever is on the right hand side in the Fischer formula, that will be placed downwards in the Haworth formula. So at C1, OH is on the right hand side, so OH will be on the below the ring, below the plane of the ring. So here at the 2, the OH is on the right hand side, so it will be below the plane of the ring. Now at 3, this is on the left hand side, so it will be above the plane of the ring. And here the at the 4, OH is on the right hand side, so at 4, right hand side means below the plane of the ring. And rest H we can place here. But there is one confusion here at the fifth carbon. What is the confusion? Confusion is here. At the C1, this ring was in one plane, but here this part is not in one plane. We cannot put in one plane. So first step should be that this was the vertical bonds, and here this is horizontal bond. So firstly we have to convert it into the vertical, so that ring should be in one plane and the rest of the group should be in another plane. And another one more thing, whenever we are drawing this Fischer formula, cyclic formula, we should draw these corners like curve. Like suppose that this is like this curve, and similarly below here, because if we are drawing these corners like this is supposed to that these are the CH2 groups. So there should not be any confusion. So that's why we should draw like this curvy bond in the Fischer formula. So here before for this, at this carbon, the lowermost carbon C5, first step should be that we should convert this bond, horizontal bond, into shift this bond into the horizontal vertical plane or vertical bond. So we can do this. We can do one interconversion, but whenever we do interconversion in the odd numbers, we get the different isomer. So if we want to get the same isomer, then we have to do interconversion into even numbers. So even numbers, so at least two interconversion we need to do, and these are also called the Walden inversion. So two Walden inversion or two interconversion we need to do whenever we are going to convert Fischer projection formula, cyclic Fischer projection formula, into the Haworth formula. So another we can do this. Firstly, in the first step we can do this, only we can draw this this much of, suppose that we have done this, and this is the CH2OH. We have interconvert this, and this is the chain here, and rest of the group I have put here, and here also this is the rest of the group. This is the first interconversion. Now the second interconversion we can do between these two groups, means we can rotate this bond, and now these can be exchanged. So that will be the second interconversion. And after second interconversion we can draw the whole structure, 1 2 3 4 5, and here this curvy bond and this oxide ring, and here this this ring, oxide ring, has come in the vertical plane, and these bonds are in the horizontal plane. And now because we are rotating it, so CH2 group will be on the left hand side, CH2OH, and here this will be H. So here H OH, H OH, H OH, and at the anomeric carbon HOH. So now this Fischer projection formula can be easily converted into this Haworth formula. Here this is 1 2 3 4 and 5. Now at 5 you can see that this CH2OH group is on the left hand side. Left hand side means that will be above the plane of the ring in the Haworth formula. So this will be CH2OH above the plane of the ring, and H on the right hand side in the Fischer formula, so that will be below the plane of the ring. And suppose that we are not doing these two interconversion, and we are just considering this H. So we will do the mistake that because H is looking like this is on the left hand side, so we will put on the H on the above the plane of the ring, and that will be a very big mistake. So whenever we are converting Fischer projection formula, cyclic projection formula into the Haworth formula, firstly we have to convert this. We have to do at least two Walden inversion, even number of conversion, so that we can get these the vertical, the oxide ring in the vertical plane, one plane, and these these rest of the groups H and OH in the uh, another plane, perpendicular plane, that is the horizontal plane. So now in the Haworth formula you can see the oxide ring is in the horizontal plane, and all the groups are in the vertical plane. So this is the Haworth formula. Now next thing is the how to convert Haworth formula into chair conformation. So this is the Haworth formula. This is the Pyranose form, the six-membered form. So now we have to convert it into the chair conformation. So the chair conformation, generally what we do, we this put this this carbon, this is the one carbon, this is four carbon. So generally we draw this conformation, and this is what this fourth carbon should be above, and one carbon should be below, means chair. We can draw the chair either this way, right, or this way, right. So this generally we draw this conformation like this: 4 C and 1, the one at the below, this part at the below, and this above. So not this one. So this is found in very exceptional cases. There are some cases which are very exceptional, otherwise this form is exist generally, this exists. And so here we will draw the chair conformation like this: oxygen, this will be the chair conformation, this is the C1, and here at C1 this OH is axial, and this there are two types of bonds, axial and equatorial. So we can put, suppose that this is the axial bond, another at another bond this is the equatorial bond, and this is hydrogen, and here another bond, this is OH is below the plane, so this will be equatorial and this is axial, and here this is hydrogen will be below and this OH will be equatorial, and similar to cyclohexane, this OH below and this will be axial, this is equatorial bond, and at this hydrogen is below axial, and this is CH2H can be written like this is, or CH2H simply. So we can draw this conformation, this is the chair conformation, or simply we can draw just like not the H, we can draw only OH like this. This is equatorial, this is equatorial, this is equatorial, and here this CH2OH bond also equatorial. Only this is the alpha, this is the axial group which is in alpha D glucopyranose. And suppose that suppose that we are taking beta, then in beta this bond also would have been this beta, means equatorial position. Now the next thing is, suppose that this is the open chain Fischer formula and we are going to convert it into the Furanoid form, means four membered ring. So in the four membered ring, this is 1 2 3 and 4, and five membered ring, not four membered ring. This is six membered ring we have discussed, which was the Pyranose form, and now we are discussing the five membered ring. This is the Furanoid structure is the five membered, because this similar to like Furanose, this is the Furanose, uh, Furanose, right. So furan, so this is similar to furan, so this is our furanoid form or Furanose. So here fourth carbon OH will attack here nucleophilically, will give the nucleophilic addition. So again there will be generation of the newly generated chiral center, so we will get the two isomer, and 1 2 3 4 5, this is the newly generated chiral center C1, and here this will be the oxide ring, 1 2 3 4, and fourth OH is taking part here, CH2OH, HOH, and rest of the groups will be at the same place, but this is newly generated, so in one isomer the OH will be on the right hand side, and in another isomer the OH at the anomeric carbon will be on the left hand side, 1 2 3 4 5. So here, and this is the oxide ring, 1 2 3 4, and this is fourth OH, and this is D and HOH. At this third, this is OH. If we are taking glucose, this is the third carbon, this is HOH, and HOH on the left hand side at the chiral center, then this will be the another anomer. This is the beta anomer. So this is the beta form, this is the alpha form, because OH is on the right hand side and anomeric carbon, and this is on the left hand side, more electronegative group, OH on the left hand side. So these are two the Fischer formula, and so these will be the B alpha D gluco furanose, and this will be the beta D gluco furanose. So these are the cyclic structure in the Fischer formula. Now next thing is how to convert this Fischer projection formula into Haworth formula, because there is the chiral center at here also. So again we should draw this in the curvy, like curvy bone, because they can be we can confused. We can consider it like CH2. So these should be drawn like a curve. And now for this also, first thing should be that the oxide ring should be in one plane before converting it into the Haworth formula. So first step should be the first interconversion, so because we want to shift it toward the vertical position, right? So here this this will be like ring, and this H, and this will be one group. Suppose that this is the group here, and this group will be here, and this is the rest of the molecule we can draw, and here also this is the rest of the molecule. And in the second interconversion, these two groups uh, may be interconverted, and now the 1 2 3 4 5 structure will be like this, 1 2 3 4 here, and no, we are doing just 1 minute. Actually we have okay, what we are doing here, 1 2 3 and 4, this 1 2 3 and 4, and now the ring will be like this, and here this is H, and this is group, this is the group, right? And this is the H here, the after conversion, and the rest of the will be HOH, HOH, and HOH. Now this can be converted into the Haworth formula. So in the Haworth formula, Furanoid form, we will draw like this, Furanoid form, and here this is the C1, this is 2 3 4. Now at the C1, OH is on the right hand side, so OH will be below the plane of the ring. Now at C2, OH is on the right hand side, so OH will be below the ring, below the plane of the ring. Now at the third position, third carbon, OH is on the left hand side, so OH will be above the plane of the ring. Now at the fourth carbon, you can see here at the fourth carbon is this 1 2 3 4. At fourth carbon, this hydrogen is on the right hand side, so hydrogen will be below. Now the group will be here. Now group, what is the group? Group is here, there is the CH2OH group. Now there is the one confusion, so where to put hydrogen and OH group, H and OH group. So for that purpose, what we can do is just we can check the RS configuration of this. RS configuration, for checking RS configuration, this is HOH and this is CH2OH and this is the rest of the group. So first priority will be given here and fourth priority for the lowest priority for to the hydrogen, and this is CH2OH. Now the second and third, the second priority will be given to this rest of the molecule and the third priority will be given to this. So we will move toward the first two, three. So 1 2 3, this is the anti-clockwise, this should be S, but because the lowest priority group is on the horizontal side, horizontal place, so that's why this will be reversed, and so this will be R. It means this is R. So R, so this should be R. It means for R, suppose that we are converting CH2OH here, this is the rest of the group, and suppose that we are putting OH here, H here, then this will be one, fourth priority here, third priority the rest of the molecule, and second priority here this, and the third priority this. So first, second and third, this is looking like clockwise, but again this lowest priority group is on the horizontal side, so that's why this should be in vertical position. So we will reverse it, means this is looking clockwise, means this should be R, but this will be S. So it means this is S, so we cannot put OH on the right hand side, so OH will be on the left hand side, this. So this will be the Haworth formula, and which is the Furanoid form. Furanoid form here. So another trick is that we will discuss that trick. Okay, before that trick, we will see that how to convert Haworth formula into chair conformation. Okay, this is the Haworth formula and this is the conformation formula. Conformation. There is no other chair conformation because this is 5-membered. For the chair conformation, we should have the 6-membered structure. Okay, so we were discussing about that in the Fischer formula. This part was like CH2OH here, HOH. This was the group, and now this is above. This was the below part, and this is we are converting like this is look like that we have rotated it, this part at 180-degree rotation in same plane. So 180-degree rotation, then this will be, this part will be like this. This is after rotation, this CH2OH will be above the plane of the ring, and at the anti-clockwise, when we go anti-clockwise, that is OH. So this is means we have rotating it 180-degree in the same plane. So when we do this, so what happens? Suppose that we are taking simply one structure CH2OH. This is the D-glyceraldehyde or D-glyceraldehyde. This is also R, right? So when we convert it, when we do 180-degree rotation in the same plane, then what will happen? The CHO will be below and CH2OH will be the topmost position, and when we move towards the clockwise of the CHO, the OH is first. So at CHO at the clockwise, OH should be here, H should be here. So you can see here, right? This is the molecule. So both the molecules are, whether both the molecules are same or not, when we can check it. Okay, how can we check? Then we can check the RS configuration. Okay, this is the first priority will be given to OH, fourth priority to H, and second priority CHO, and third priority CH2OH. So first to third movement is anti-clockwise, so it should be S, but because lowest priority group, that is the hydrogen, is on the horizontal position, that should be in vertical position, so we have to reverse it, so it will be R. So this is R configuration. Now we can check it here. First priority OH, fourth priority H, third priority to CHO, and second priority to CHO, and third priority to CH2OH. Okay, the first, second, and third, this is anti-clockwise, so this should be S, but again hydrogen, which is the least priority group, so that is on horizontal position, that should be in vertical position, that is the rule. So for converting it, it will be reversed, so it is looking S, so this will be R. It means both the structures are R. It means rule is this, that whenever we are rotating any molecule in the same plane, we will get the same molecule. And when we rotate any molecule 1 by 180 degree in the perpendicular plane, the molecule will change, right? So this is the rule.